Welcome to Mars Saga, your gateway to the Red Planet. Subscribe now and join the journey.
Mars Saga continues its exploration of the Red Planet by moving beyond the visible surface and focusing on what lies just beneath the dust. While Mars may appear quiet and unchanged, its subsurface tells a deeper and more complex story. Beneath the thin layer of dust and rock exists a record of internal activity, buried ice, ancient fractures, and chemical processes that shaped the planet over billions of years. The outermost layer of Mars is called regolith. This layer is made of crushed rock, dust, sand, and fragments created by impacts and erosion. Unlike soil on Earth, Martian regolith contains no organic matter produced by plants or animals. Instead, it is purely mineral in nature, formed by mechanical and chemical breakdown of surface rocks. Regolith thickness varies across Mars. In some regions, it is only a few meters deep, while in others, it extends for tens of meters. This layer acts as a protective blanket, preserving older geological features underneath. Because Mars lacks frequent earthquakes and heavy rainfall, buried layers remain largely undisturbed for long periods of time. Below the regolith, Mars reveals sedimentary layers formed in different environments. Some layers formed in ancient lakes, others from volcanic ash, and some from wind-driven dust accumulation. These layers stack over time, creating a timeline that scientists can analyze to understand environmental changes. Radar instruments orbiting Mars have allowed scientists to peer below the surface without digging. These instruments send radio waves into the ground and measure how they reflect back. Differences in reflection reveal variations in material, such as rock, ice, or sediment. This technology has confirmed the presence of buried ice in many regions far from the poles. Subsurface ice is one of the most significant discoveries on Mars. In mid-latitude regions, ice exists just beneath the surface, protected from direct sunlight by a thin cover of soil. This ice likely formed during periods when Mars' climate was different, and its axis tilt caused ice to migrate away from the poles. At the polar regions, layered ice deposits extend deep below the surface. These layers contain alternating bands of ice and dust, similar to tree rings on Earth. Each layer represents a period of climate change, recording shifts in temperature, atmosphere, and dust activity over millions of years. Beneath some regions of Mars, scientists have detected features that resemble buried river channels and ancient flood paths. These channels are no longer visible on the surface, but remain preserved underground. Their existence suggests that water once flowed across the planet in large volumes, reshaping the landscape before being buried by later deposits. Mars also shows signs of extensive fracturing below the surface. These fractures formed as the planet cooled and contracted over time. As Mars lost internal heat, its crust cracked, creating networks of faults and fractures that allowed fluids to move through rock layers. Evidence suggests that groundwater once moved through these subsurface fractures. Mineral veins found by rovers indicate that fluids carried dissolved minerals and deposited them as they cooled or evaporated. These veins act as proof that water circulated below the surface long after surface water disappeared. The chemical composition of subsurface materials is different from surface dust. Beneath the oxidized outer layer, rocks often contain less rusted minerals. This suggests that subsurface environments were more chemically stable and shielded from harsh radiation. Radiation is one of the most destructive forces on the Martian surface. Without a thick atmosphere or magnetic field, cosmic radiation constantly bombards the planet. However, even a few meters of soil can significantly reduce radiation exposure. This makes the subsurface one of the most stable environments Mars has ever had. Because of this stability, the subsurface is considered one of the best places to search for preserved signs of ancient life. Organic molecules break down quickly on the surface, but underground they can survive for billions of years. This is why future missions aim to drill deeper than ever before. Mars's interior structure also plays a role in subsurface features. Beneath the crust lies a mantle made of dense rock. Although Mars is mostly inactive today, evidence suggests that its interior was once much hotter and more dynamic. This internal heat drove volcanic activity and influenced crust formation. Seismic data from landers have revealed that Mars still experiences small tremors, known as Marsquakes. These tremors indicate that the planet is not completely geologically dead. Internal stresses continue to reshape the crust slowly, affecting subsurface structures. Volcanic activity contributed significantly to subsurface layering. Lava flows buried older terrain, sealing in sediments and altering surrounding rock through heat. In some regions, volcanic heat may have melted underground ice, creating temporary liquid water environments beneath the surface. Such environments are of particular interest because they could have remained warm and wet long after surface conditions became hostile. Subsurface hydrothermal systems are known on Earth to support life without sunlight, relying instead on chemical energy. Mars also contains thick deposits of sedimentary rock that formed from long-term accumulation of dust and ash. These deposits compacted over time, turning loose material into solid rock. Pressure and chemical reactions altered these layers, preserving chemical signatures from the past. Some subsurface layers contain salts, such as sulfates and chlorides. These salts form when water evaporates, leaving minerals behind. Their presence underground suggests that water once moved through these layers and later disappeared. In certain regions, radar data have revealed bright reflective layers deep below the surface that may represent frozen brines. These brines would be extremely salty and cold, but they represent one of the few possible locations where liquid water could still exist today, even temporarily. Subsurface exploration also helps explain surface collapse features. Some pits and depressions on Mars form when underground material shifts or ice sublimates, causing the ground above to sink. These features reveal active processes still shaping the planet. Understanding the subsurface is critical for future human missions. Underground ice could provide water for drinking, oxygen production, and fuel generation. Subsurface habitats would also offer protection from radiation and extreme temperature swings. Robotic missions are already preparing for deeper exploration. Drilling systems are becoming more advanced, allowing rovers to reach below the radiation-damaged zone. Sample return missions aim to bring subsurface material back to Earth for detailed analysis. Mars's buried history is vast and largely untouched. Each layer below the surface represents a chapter of planetary evolution that has not been erased by weather or plate movement. This makes Mars one of the best places in the solar system to study early planetary conditions. The subsurface connects the planet's past to its future. What lies beneath the dust may explain how Mars transitioned from a warmer, wetter world to the cold desert seen today. It may also reveal whether Mars ever provided stable environments suitable for life. Mars Saga continues to uncover these hidden records, moving beyond what the eye can see. The red dust hides a deeper truth, written in layers of stone, ice, and time. Beneath the surface of Mars, the story continues. Thanks for watching. You were watching Mars Saga.